Yes, good morning, good afternoon, good evening, wherever you are in the world. Welcome to this webinar session. This is actually an expert session, 1 hour expert session on EpanetJS entitled Water Modeling Reimagined. We are the Philippine Young Water Professionals, and we are hosting this session in collaboration with our partner, Iterating, and we have our speaker, Luke Butler, here with us. Okay, we'll give other people a few seconds to join, and then we'll start. Okay. Just to ensure that you have a good experience with the session today, we have a few reminders for our webinar. Please keep your microphone muted at all times. However, we encourage you to have your video feed on if you want. So this would feel real and more interactive. There would be an opportunity for Q&A after the presentation and the workshop. We will leave a prompt in the chat box for you to type your question once the floor is open for the Q&A. And lastly, for any safeguarding concerns, we understand that this is a public webinar, so just please drop a message in the chat box to call the attention of the Philippine Young Water Professionals Steerco. Start your chat with the phrase safeguarding concerns so that we can attend to your needs. Before we move on to our session, I think we have a pre-survey poll. MJ, if you can start the poll just to understand where everybody comes from and what best describes you as a participant in this session. We'll give you around 20 seconds to answer the survey. If you can please answer that survey, it will be very helpful for us in understanding the analytics from this session. Very good. We're getting into 50% of the participants respond. A few more. Come on. Very good. Oh, we're now at 71 people. Thank you so much for making time to attend this session. We really appreciate it. I think that's it. Thank you, MJ. And just to break the ice, I know everybody's maybe coming from different time zones. So we promoted the event a few weeks ago. I'd like to know how you're joining us today. Kindly drop an adjective or emoji in the chat box that best describes the feeling of you, like how you feel coming into the session today. So I hope that makes you more familiar with the Zoom platform and also help you break the ice. And because later you would be using the chat box function for your question. So yeah, hopefully that makes you feel a little bit more relaxed and calm. All right. Without further ado, I would like to introduce our speaker for today. Oh, thank you very much for joining us, 10 o'clock in the evening where you are. Luke Butler, co-founder of Iterating. So Luke Butler is a hydraulic modeler and software developer from Canada with over a decade of experience in the water industry. He's one half of Iterating, the startup that developed EpanetJS, and we are very lucky and really honored today to have Luke as our mentor as we navigate through EpanetJS. So without further ado, I'll hand over the webinar controls to you. Luke, welcome to this webinar session.
Yeah, thank you. Thank you so much for having me. Let me just get my screen running here, and then that should be up. Yeah, so I'm Luke Butler. I'm really excited to be here. It's a little later for me. It's 10 p.m. here in Canada and in Toronto. But I'm excited. This is the first webinar that I'm doing as iterating and talking about EpanetJS. So it's a privilege to be able to do it with everybody here. And then you can let me know how I go. But yes, very proud to be able to talk about something that I've been working on publicly. Well, publicly only for a few weeks, but privately for quite a while. Yeah, so a little bit of background on myself. So I'm a civil engineer. I've been about 15 years in the water industry, so always sort of in the water industry. I've done work. I'm originally from Australia, so I started off in Australia working at a water utility. Eventually, I moved to the UK and I worked at a consultancy for a couple of years. Actually, during this period, I was always doing water modeling. There was some attachment to water modeling. When I was in the UK, I was doing it as a consultant, working for UK utilities. And then I ended up moving to Canada. I met my wife, who was Canadian in the UK, and we moved to Canada. And we've been here about 7 or 8 years. And then I kept doing water modeling when I moved to North America. It's a little bit of a different experience. They do it slightly different every place that I go. But then I ended up leaning more towards the software development side. So I've always done coding and programming, but I was started to build more tools around automation. I ended up working towards working at a Spanish company that was doing digital twins, hydraulic modeling, sort of this new generation of tools. So I did that for a bit, and now I've branched off and creating our own set of tools. You'll see plenty of that here, and under a new company called Iterating, and we're developing epanet-js, a new, to say, the next generation of hydraulic modeling tools for the traditional users, the engineers. I'm one of two people in this company, and I think it's important to also acknowledge my second half in here, which is Sam. So Sam is let's say that the coding brains. While I can code to get something together, he's the one that's really pushing everything forward. So we make two halves of this equation. A little bit of an agenda today. I'm going to start with a little bit of background. What is hydraulic modeling? I assume that there'll be some people here who are familiar, some who aren't. So I'm going to start on a baseline that is you may be not aware. So, this may be common knowledge to some of us, but I think it's good to get that baseline from where we're starting. I'm going to then do a little demo of epanet.js so you can sort of see where we are in association to other sort of tools. And then one of the things we're actually building in this tool, you'll see, is we're making this actually open source. All the code is available to everyone. And we'll go into a little bit more detail on why we're deciding to do that, which is maybe a little bit of an unusual move that some people might consider. I think it's a very valid one, but we'll see. And in the end, we'll go into sort of a more interactive workshop. So we're hoping that this first part is about 20 minutes, and then really spending a lot of time actually in the tool, learning some practical doing some practical exercises that you can follow along with, and then also learn at the same time. So we will ask you sort of around this midsection to try, if you've got two screens and you can manage, try and open up the tool, getting yourself started, and then we'll follow through an exercise together. And then I'll pick up and do some more complicated stuff that maybe is slightly harder to do in this virtual environment. So with that all said, let's get into, what is hydraulic modeling. So hydraulic modeling is sort of like a discipline, a specialty skill within the water industry. And it's all about using specialized software to run simulations of a water network. It's a tool that engineers or specialized trained hydraulic modelers can do to understand how a water system is behaving and reacting to changes. So essentially, it allows you to represent the water network in a digital environment and sort of ask what if questions and see how, like I said, it responds, right? So you see a couple of tools here, trusty epanet, he's here on the left, and then a couple of two of the big commercial tools, one by Bentley Water Gems and then one by Autodesk InfoWorks here. They all sort of have similar things. You have a map sort of that where you can see the network, so like your GIS, and then some ways to report back information, so like you can see pressures and flows, and that's really what you're trying to do with this model, right? Being able to understand where is the water flowing throughout your network. So how is it going from your tanks and pumps to your customers? Which pipes is it going down? And what pressures are you finding out throughout your network? And the real power comes from not just being able to represent the system it is now, but giving you almost like a crystal ball or a what if tool, right? To be able to say, what if something changes? Like what happens if there's more demand? What happens if we change something? And then you can see how your system will react before you do it in person. And really there's, I would say, three main categories of what ifs that you can do and that make up the bulk of how people use hydraulic models. So the first is planning. It's all about let's say this is probably the most traditional use case of hydraulic models, right? You have a water utility, and they want to understand we have a water network, and over a period of time, generally 20 or 30 years, the network is going to grow. We're going to get more people in the system, and we need to understand how the system will be able to cope with that extra growth, and will there be enough capacity in the system to handle that? Or will we have to build extra infrastructure to deal with it? So like either upsize mains, build new mains, add tanks, add pumps. And the hydraulic modeling tool is very powerful in this respect, where you can, build it out over a period of time. So, okay, what happens in 5 years, 10 years, 15 years, 20 years? And then this usually gets packaged together all in a nice little report. This one here is an example of what they call a water master plan, where the utility can figure out, okay, what are we going to be building over the next 30 years, and they can prioritize work and make sure that they have enough funding to do that. This is pretty typical in North America. I mean, it's typical everywhere, but this is the default case in North America. And generally, they'll do this every 3 to 5 years on each of their networks, right? They'll recycle and make sure that their plans are working. So this is probably what you call the bare minimum of hydraulic modeling, this planning. The next step up is what I would call operational modeling. In this case, instead of just worrying about what's happening in the future, you've built this tool to give you this crystal ball into how your system is working now. People can use it to solve operational challenges of the current system. So it could be maybe they're seeing deficiencies or they want to make some changes. They can use the hydraulic model to test out different scenarios before they change the system as it's currently running. So maybe, for example, they're finding low pressure, and so they want to change some settings on a pump, or maybe the opposite, the pressure is too high, so they want to look at modifying a pressure reducing valve, or maybe they have high leakage and they want to move some monitoring zones and move some boundaries around. These tools are usually used by engineers or those highly skilled on behalf of operators to understand the network and provide advice. And so it goes from something that's put on the shelf and pulled off every 3 years to something that's used almost day to day to support the water utility. This type of modeling is very strong in Europe, and a little bit so in Australia. I'm not actually as sure in parts of Asia. I know actually in Philippines, I see lots of hydraulic modelers, so I assume they're doing this type of work as well. But this is generally a much more advanced type of modeling. Where the really trendy people are at the moment is what we call live modeling, or what is more commonly now referred to as digital twins. Maybe you've heard the phrase digital twins. It's really taking that operational model and taking it to the, let's say, the next level, where instead of just doing an average day and representing that, you're trying to take information from your remote monitoring systems, your SCADAs, your telemetries, where you're monitoring the different components of your system, and feeding that into the model so that you end up having a complete digital replica of your system, in the sense that whatever's happening in the field is happening in parallel in your system. So when you've got your big control room up here, you can also have a digital model that is showing you deeper into the system than what you could see with your sensors. And then this is generally paired together with a predictive side as well. So instead of just figuring out what's happening now, they'll do some predictive work on what's going to happen for the next 24 hours. What's the weather like, what's the demands, and it will figure out, okay, what the consumption will be over that period, and then feeds that into the future, so that the operators aren't just seeing what's happening now throughout their whole system, but they get a peek into the next 24 hours, right? And then they can make decisions on that and see how it would potentially affect the system going forward. So this digital twin is all the rage. It's what everybody is doing, partly because the planning models, operation models have been solved, and a lot of them I would call on maintenance mode. There's not much to be added. This is the new green field that everybody wants to get into, right? Getting these models, giving them to operators, new people. It's the new exciting way to expand our territory and get more people in. So this is getting a lot of love. Not so much the planning tools that I would have typically used. They're a little bit stuck in the past, but this is where most of the excitement is. And this is sort of what I've been working on for the last few years. Now, that's the overarching picture of the hydraulic modeling space. I wanted to go back into a little bit on what EPANET is, EPANET or EPANET, depending on how you refer to it. You might have heard that. And why are we talking about this and why are we named the new tool after it? Epanet is that little funny tool that we saw at the start. It looks like something out of, Windows 95, something out of the 90s. Because honestly, it sort of really is. It was like it hasn't really been changed since the early 2000s. But this tool, many people, if you don't know what Epanet is, but you know hydraulic modeling, you might discount this as something that's not a serious sort of application, maybe something just academics to do little sketches. But really, the power in Ethernet is the engine itself. While this application looks relatively simple, there's a very powerful hydraulic modeling engine that goes behind it, which some people might refer to a black box, but I don't think that's a fair description. This hydraulic modeling engine is actually an open source toolkit developed by the US EPA that is well documented, well studied. It's used quite extensively by the sort of academic spaces to do sort of studies and other things. And what this engine allows you to do is actually to embed it inside other applications or run it in other processes like Python and that type of thing. Um, and this is the tool that was originally developed by the US EPA and then extended out to become fully open source. And the way that it sort of works is that you have a model. So you define how your network looks, like how it's all connected, what the demands are. You push it into Ethernet, and it will give you those results back as it will say, okay, well, this based off what you've told me put into the box, what comes out of the box is what the pressures and flows are. And actually, so that little antique looking piece of software is sitting on top of a very powerful engine. And that powerful engine actually ends up powering pretty much all the commercial tools that exist at the moment, with the exception of InfoWorks WS Pro, which is their own thing, but that's a little side note. But basically, everybody that does hydraulic modeling through some extent uses Epanet or some derivative of it, right? So everybody is working off the back of this very powerful hydraulic engine. They just have a much flashier front end. Now, if I was to categorize the tools and I was going to put them in this little 4x4, 2x2 matrix, and you would say, okay, what is the features of the tools you have? So something that's very simple that maybe doesn't have too much things, but it sort of does the job. You have powerful up on this side. Sorry. And then on the left, you've got free, and to the right, you've got expensive tools. Ethernet being totally free, obviously sits right here on the left-hand side, but it is relatively basic. It has a lot of powerful features, but it is quite difficult to use. It doesn't have everything that you would expect, like integration with mapping or live data, or being able to like clean up some of the data sources that come through. But like I said, it doesn't cost anything, so that's a huge benefit. And then all the way on the other side, this is just a mock-up. This I'm not pointing at anyone in particular, but you have quite expensive software, but very, very powerful software. Very powerful software that can solve these problems by giving the utilities all the right tools to get things done. So things like integrating with a GIS system, being able to make it easier to compare different scenarios, different versions of the model without having to like open multiple copies. But that comes at at a price, right? We're typically looking for this software in US dollars, somewhere around 10,000 US dollars per user per year. So quite expensive. The vendors will say, well, you're using it to plan millions, if not tens of millions or more worth of infrastructure. So what's $10,000? And that's fair for some of the larger utilities or consultants, but it doesn't scale back down to small utilities or those who aren't in, let's say wealthy Western countries, right? You end up with a lot of people in other places of the world or small utilities being forced to use this because this is their only option. One other axis I would love to throw on here down the bottom is not just cost, but accessibility. So we have on one side complexity, and then the other side ease of use. I would say Ethernet is relatively easy to use, mostly because there's not much you can do with it, and most people would associate easy and simple together. But a lot of people also put these powerful tools together with complexity, and they sometimes they say, well, a powerful tool has to be complex. If you like look at these, they've got millions of buttons, millions of options. It's so powerful because of the complexity. But I think there's an alternative version of these hydraulic modeling tools that could exist in this little square up here in the top left-hand corner. What happens if we had the powerful tools that we needed to get the job done without the complexity, without having, some of these tools have like two or three different ways to do the same thing. Generally, if a utility brings in a new set of tools, the first thing they do is they set their engineers on a 2-day training course just how to use the tool. What happens if we built a tool that was intuitive to use, easy to use, but still powerful? And that's what me and Sam really wanted to do. We wanted to build a hydraulic modeling tool for hydraulic engineers that took away some of the complexity that is inherent in building a hydraulic model, but then also make it accessible and affordable option at the same time, trying to really shake things up, living in this little box here. So that's where we decided to make a new alternative, right? So the previous versions were all desktop tools. Could we create something that was web-based, really easy to get into? You just go to the browser, you open it up, you can start drawing models, making changes, and really providing something that's a strong alternative to the status quo. So I'm going to jump into the tool now and show you it. What I'm going to suggest is, I don't know if you want to also put this link in the chat as well. And then maybe while I'm just doing a quick demo, people can try to open it up and see it themselves. I'll bring it across to here. And what I'm going to do, I'm going to spend maybe 2 or 3 minutes just showing it around. And then after that, I'm going to talk a little bit more. But maybe during that period, if people want to come to this site and get themselves ready in here and then optionally register as well if they like, totally optional. That's one of the things in the app itself. We don't require anyone to log in to get to use the tool. We want, like I said, we really want to reduce friction. So you can go straight from that landing page into the app. And you can see here, we even want to make it easy that you have an example. We give a couple example screens. And straight away, with just a couple of clicks, you can see an example network in front of us. I will throw one little pitch. If you do want to register, it would make me really happy. You get a couple little benefits, like you get high res satellite views. It makes me feel good when I see more people registering, and you'll get one email a month from me telling you where it's progressing. But if you don't want to, you want to do it all anonymously, I'm okay with that. Like I said, it would just make me smile seeing people register. So that's my only little sales pitch at this moment. So here we go. We got our little hydraulic modeling tool. We've got our little network in front of us. We can, start to click on some of the elements. We can see, here's a pipe. We can see information about it, like the size, the roughness. If we click on a junction, we can see how much demand is coming at those locations and its elevation. But where it more gets interesting is when you run a simulation. So if we press this simulate button, we can see the simulation was successful. And now when we look at any of these pipes, we can start to see some simulation results like flow rates and pressure. And so instead of clicking around, what we want to do is be able to visualize that on the map. We've got this map tab here. You can go, okay, I want to see what the pressures in the system are. I want to see what the flow rates are. And straight away, you can see you've got some nice visuals of the pressures that's changing throughout this network. I should also mention, if we drop to the satellite view, you can see there's an elevated tank here. And then this is at the top of the hill, and then this is supplied with gravity. And as you go further away down the hill, the pressure will increase. So we can sort of see, we've got the large amounts of water come through these large mains, and they supply these areas. So just trying to make it easy, get in a model, run a simulation, see some results. And the same in being able to modify or change it, right? Pick up a pipe. If we want to draw a new pipe, we can, click around. We'll go through in more detail how we do this soon, but you can click this. You'll say, okay, well, simulation's out of date because we changed it. We run it. New simulation. We can see some flow moving through these new pipes. We could isolate a section by like closing a pipe section down. So we've isolated this. Run it. You'll see that the water's moving the other direction. Making it really easy, just a couple of quick controls and changes to get this done. If you had used the other commercial tools, maybe this seems very simple in comparison or very easy. The other tools can be a lot more involved to even do these simple things. A couple of other benefits that if you're an Epanet user, one of the things that people really love is undo redo. Once again, people see this as, undo redo, very simple. But this has been a missing feature from Epanet since the beginning. If you make a mistake, you're stuck. You just have to do it again. but yes, we're just trying to create this nice web-based tool that anyone can get into modeling. And now the big curveball on this is we also made the entire thing open source as well. So this tool, not only is it free to get in and use, there is a paid version, but we are actually giving away the entire code for the application too. We're giving it under special license, and I'll talk in a second, but we want to fundamentally change the way that people approach hydraulic modeling software and give an alternative future for us as engineers in this space. So let me jump back into my little presentation here before we get into the exciting part of actually trying to do some modeling. Um, I guess the lot of questions people ask is like, okay, well, I can understand why you build this tool if you look at it from a marketing or business point of view. Like there's some free software, some expensive software. That little quadrant there seems like a great business opportunity. But I do hear this from a lot of people like, why are you throwing it away by giving it open source? Um, but I think really it goes back to the premise on what Epanet is and what we're trying to achieve here. So I'm a contributor to the Epanet engine. I work with the open source engine and try to give back. And the way I see Epanet is a gift to the water industry. It's a gift by the US EPA for a free and open free and open source hydraulic modeling engine that was actually the foundations for all the commercial softwares within this space. However, it ended up being a bit of a broken promise, or maybe a gift that wasn't truly received very well, because all the people in the commercial industry end up not contributing back, while others in other industries will typically support the open source tools that are core to them, like so in say the gaming or music or video industry. It hasn't been the case here in engineering. If anything, they've built their private tools and they've actually end up locking it away with proprietary licenses and software patents. So they build on top of these public works, profited from them, and then actively discourage others from moving forward, right? So either by locking things away with software patents or discouraging the US EPA from improving the user interface to keep their versions sort of leading the charge. And this sort of left the community with stagnant tools while they were able to make charge quite high prices for these modeling tools. Yeah, so they basically commercial vendors privatized the improvements on top of Ethernet, and it left us with like a false choice. These users of hydraulic modeling, right? Either the choice that seemed to appear to them was either we use these outdated free tools and make workarounds and try our best, or we have to pay for expensive bloated software. And I think this approach, not only is it penalizes those with small budgets, it also it stifles innovation within this field too. So our goal, as we saw it, is not just to build software. And we thought this whole process of leaving open source behind was we didn't think open source should be an afterthought. Instead, we thought it should be the goal itself, right? We wanted to be able to give an option to be able to contribute back into Epanet as that gift to the water modeling industry. So we wanted to develop a modern, affordable tool that was powerful, that could create a sustainable option for the engine that we all depend on. And we wanted to give people who love the Epanet project and the open source core a way to contribute back, even if they couldn't program or they weren't a researcher. We wanted to be able to say, if you support our tool, you're supporting a tool that supports Epanet. And the way that we see that coming together is by building a new model. So we refer to as a better model for modeling and a sustainable open source option. And the way we see it is we provide people with a free and open source app to use hydraulic modeling. Some of the people who use the app will decide to pay for some of the more advanced features or services within there. We want to give as much as we can away for free, but there are some core features we know larger users will depend on. So we'll offer those as an extra charge. That extra charge ends up becoming income for the developers of the project, and that can be reinvested in the project itself. So at the moment, that's me and Sam, but we also want to then extend this out to other contributors of Epanet. This income and reinvestment in the project allows the app and engine to get better over time, which then allows more people to discover and use the app, which then becomes this nice cycle where more people can use open source, more people pay into it, and then we contribute back and it creates a nice little circle. And this is what we refer to as a sustainable, open source sort of practice or principle. Now, one of the things some people might worry about is, oh, if we publish all this code, won't someone just take it and compete against us? Probably. Like, honestly, knowing people's the history of the industry, it would seem like a foolish thing to do. So we are using a special type of software license called the functional software license. And the way that this works is that the code is available from day one, but it gives us the exclusive license, commercial license of the code for 2 years. It allows us to commercialize it and not allow others to compete against us or do anything that might be harmful to us. But then after a 2-year period, that code then transitions from this semi-public open license to a fully open source code on the MIT. And what happens is every time we write code, that 2-year clock starts on that new set of code. And so basically, it means that if people know that they invest their time or choice to use this tool, that in 2 years' time, it's not just a perpetual license they've got, but they will actually own the entire code, will be open for all. So if me and Sam get bored or do something else or get bored out, that code is then available for all. You just have to wait 2 years and then someone else can pick up where we left off and continue on. Or maybe more interesting, maybe they come up with a new innovative idea that this can be the basis of that then they can extend out to more things. Maybe they want to do asset management or a leakage tool, but they don't want to deal with all the drawing the network and that tool. We give them a good basis that they can do that. We think this approach creates the biggest balance between us having the incentive to keep going, because if we stall them for 2 years, someone else can just pick it up. And actually, because of this license, if we just sat there and did nothing and just charged prices, in 2 years, someone could start selling the code. It would be okay. That would be, using it for commercial purposes to compete against us would be fine. So it gives us the incentive to move forward, improve it, and it sort of probably gives a lifetime for this project itself. So a little bit, I'll go back, a little bit, I think crazy is the wrong word, a little bit groundbreaking maybe in this industry. But we think someone has to make this first move to make this change in the industry. And then it's that either Sam and I are the most brave or foolish, but we will find out. But we think the end result will be that we'll be able to provide a tool that benefits everyone throughout the industry without a doubt. So like I said, we'll open up for questions later. What I think we can do now is maybe start doing a little bit of some worked exercises of sort of the things that you can do in this tool. I will take a moment. Let me just open up EpanetJS. I will log in because I like using the satellite view. Just give me a second. Okay, perfect. I'm in. Okay, so hopefully everyone's had a chance to load up the application. I'm going to go relatively slow. So hopefully you have two screens, you can follow along. And what we're going to do is we're going to do two exercises. One is we're going to, say we're in charge of the water utility and we have a development inquiry, somewhere we wants to extend a network and they want to confirm if they are able to supply this area from this water tank, right? So we can say we put on the satellite view, we can say, okay, somebody in this area over here wants to know, could we extend the network up and around here? And would there be enough pressure and supply to do that? And then the next thing we'll do is also what we call a fire flow analysis. So let me just refresh. So when you get into the app, you should see two demo models. We want to be able to click the drum chapel. So this is the UK model. So we'll select this one. I will keep giving little breaks in between so you can follow along. What we now want to do is zoom into this area here. So up in the northern section, and we're going to extend out this network through this little block and up and to the right. So the way that we can do that is we can zoom in a little bit and we want to draw our network. The way you can do that is you can come up here and you see in the toolbar we have a pipe. So we're going to draw a new pipe in the network. We can select that. And then we're going to start in an existing location. So we'll just draw this little square to start with, make it nice and easy. So we'll click here to connect to the junction and you have what we call a rubber band. And to finish, because it's a nice straight line, we can just double click and that will bring it in. If you single click, it will create a vertex. So you can press escape and try again. So you could select and delete it. But we can select here, double click, and what we'll do is we'll connect all these dots so we get a nice little square. At this point, it's drawn those bits in. We could change the pipe diameters and sizes. We'll leave them as defaults. One of the nice things about EpanetJS, we want to make things quick. So we actually check the elevations for you and set those. Other tools, you'd have to write those in or get some data, but we already set those elevations. So if we run the simulation now, hopefully you've all drawn this little square. You'll see the simulations run successfully. And then we're going to just inspect what the pressure at these locations are. So we can do that in two ways. We can either select the junction, and you can look over here and you can see what this pressure is. It says it's 37 meters, or it should be approximately 37 meters for you. And that would be acceptable amount of pressure. Like generally in the UK, as long as it's above 20 meters of pressure, that is an okay amount of water. It depends where you are in the world, but it may or may not be. The next thing we can do is do some visualization. And I'll take a little pause after this because I know maybe I'm moving quick. I'll give everyone a second. Hopefully you've drawn this little point. You want to go across to the map tab. And then we have our options to color nodes or links. We'll start by coloring the node. So we can go color by, we'll do the drop down, and we'll do pressure. And when you select that, it should automatically give you some options here on like, well, it should set some defaults for you. So you'd be able to see some, where there's high and low pressure, as we can see, sort of things look okay here. Hopefully everyone's done that. You could also turn on labels too, so you could see, roughly what the pressures are as well. The last bit is we're going to extend this up and around the corner to here at the end of this road and see, okay, answer the question is there enough pressure to supply in this area? So we'll go back to get our pipe tool. We'll select here and we'll go around the bend. So you can either double click to add a junction, or an alternative option is if you hold down the control key or the Apple key or whatever it is on Mac and you click, it will actually drop the junction for you. And then you can keep clicking as well. So you can either double click or you can hold control and continue. We'll get through. And now we've extended the network up and around the corner, right? So this is a pretty typical thing where people will ask us, okay, can we service a new area? And at this point, we can run the simulation. And then we can make an assessment on the suitability of being able to service this area. Hopefully, I'll give everyone a second. I'll take a quick drink, and then we can see what we think. Okay, so hopefully you've followed along, but yeah, it's basically we've drawn this section in. We should be able to see some pressure here now. And it's probably, if you've done it correctly and you follow along, given about 15 meters of pressure. And this is without even including any extra demand in this area, right? Typically, you would also be adding a little bit of flow through here. Maybe we can do, let's say 0.1 of a liter to simulate some water coming through the pipe. Because we use quite a large pipe, it's probably not actually going to affect things. But this pressure in itself is quite low and probably a little bit concerning if it's below 20 meters. So I think with this, you can make an assessment quite quickly that this tank that's at the top of this hill here wouldn't be able to service this region here. It's like the elevation is getting too high and getting too close to what the maximum level of this tank is. So just a quick sort of example of what you would do in a hydraulic model, right? Put some new infrastructure down, change some demands, and then make an assessment on if it is possible to service an area. Also said at any point, if you make a mistake, remember you've got undo, redo as well. We'll do one more little example of something that you could commonly do in a model. I'm just turning off these visualizations, but it's up to you if you want to keep it in. Another thing that's common, well, it depends on where you are in the world, but sometimes engineers will do what we call a fire flow analysis. So you'll have a fire hydrant in the street in some capacity, and then you'll get an inquiry, okay, what's the maximum amount of flow that we can get out of this fire hydrant? And so hydraulic models are a very handy tool to do this because the alternative is going out there and turning on the fire hydrant and getting lots of water going everywhere. Models are a nice tool to be able to ask these sort of what if questions. So um, you can really pick any junction, but I want to show you quickly an example of what it's going to look like. Just give me a second. We won't actually draw this curve, but what you can do is you end up developing a curve that looks sort of, I'm just opening another screen, my little example here. Oops, sorry, apologies, clicked the wrong one. Um, Down here, you get this sort of like curve, right? Where the utility will ask, okay, as we take increasing amounts of water from the system, how is the system reacting? And as you draw and draw more water, you get this sort of exponential drop of pressure. And so you end up being able to draw this curve to say, okay, as we take more and more water from the fire hydrant, how is that system reacting? So we can do a little quick exercise of trying to do that as well. Pick a location and then see, okay, as we increase the flow rate, how does that system cope? So say, for example, we can pick anywhere. What's this? This is probably a tiny little street. Yeah, I'm going to pick this end junction here, but you can really pick anyone that you want. The smaller the pipes, the less water you'll obviously get through them. But what you can do is, we'll imagine there's a hydrant here. The first thing we want to do is take note of what the existing pressure is. So we're about 45 meters of pressure, and we'll slowly ramp up that to help draw our curve. So we'll start at 5 liters a second, and then we'll rerun the simulation. So we can click here, and we can see that's dropped from about 45 to 40 meters pressure. And then you'd write this down in a little Excel to get for your letter or your graph. And do say 10 next. So we ramp up the flow a little bit more. Press simulate. You can see now this has dropped quite rapidly. Before, when we did the first 5 liters a second to drop 5 meters, we did another 5 liters. It's dropped 10 meters this time down to 30. If we now do 15, I'm going to assume it's going to be quite low. It's dropped, 13 meters this time. So it's dropped even further to 17. And generally this would be, normally when they're doing these flow tests, they usually target, okay, how much flow can we get out at 20 liters a second, right? That's a common question, like how much water is available for firefighting services at this location for 20 meters, right? So you can sort of draw that nice curve and figure out that number there. And so, yeah, these are like very common things that you'll do in a modeling exercise. And there are some other tricks to do some more complicated things. I know we're getting close to time. We've probably got about 7 more minutes before maybe we want to open up for some questions. So what I'm thinking is I'm going to jump into leading some exercises directly. And you don't have to follow this one through. What it actually is on the Help Center of EpanetJS, there is this worked example. I'm just going to show a couple examples on here. This is a nice one where you actually build out a water network in the US, and you know not only do you design a network, but you do some fire flow analysis and design a pump. After this, if you want to learn a little bit more of building a real water network, this is a nice example that you're able to follow. So I will quickly run through that. Yeah, like I said, if you want to keep messing around with it, you can. Otherwise, like I said, I'm going to just quickly show a more, let's say, complicated example. What I'm going to do for this one is I'm actually going to add the base map on here so I can trace the network. Typically, you wouldn't be tracing a network, but it's more for like demonstration purposes. So we will add this in, and then I'm going to have to zoom all the way out of the world to find our network. Luckily, we have this little dot here. And this is a little rural town in Kentucky called Wheelwright. You can see there's one tank and one treatment plant, and you can see it's relatively simple. Maybe there's like 500 people that live in this area. It's like quite between sort of like these mountain passes, and yeah, you have a tank up high and a pump from a well that pumps into this tank and then supplies down. So what I'm going to do is I'm going to really quickly just draw out this network. Typically, you would import this in from GIS, but I wanted to show you how quickly we can do this even from drawing. So we have the storage point. what I'm doing is I'm going to add the tank there. I'm just going to change parameters. So I'm going to change the size. I know it's say like 10 meters tall. I will say it's about 5 meters full. I know it's a say a 10-meter wide tank diameter. And at this point, I'm just going to start drawing some pipes, right? So I'm just going to do this relatively roughly but quickly. And you can see as we zoom in, like I said, this is going to be rough, but it will get the job done. And then we can, what we'll do is we'll get down to the reservoir, sorry, this is the water supply area. So where they have the, what's it called? The wells that they pump and treat water in. So like I said, this is going to be the roughest network ever. You could probably spend more time doing this correctly. I'll draw this one here. See how quickly I can sketch this network. There, here. I think I'm almost done. I'm just going to do this around this one little corner and do this here. Oh, yes. And then, sorry, I'll just get, what we're going to do is actually bring in the demand. So at the moment, if we run this system, there's no customers using any water, right? So it will tell us what the theoretical maximum pressure is at any of these locations. But it won't be, let's see, here we go. Perfect. How quickly can you draw a rural network, right? So even this, you can get a network going pretty quickly. As you probably saw in the other one, we automatically determine what the elevation is, so we know the tank is up high. And so even from this really rough sketch, we can get a good representation of this network, right? So if we now run the simulation and we look at pressures, we already know, okay, what is the pressures within the system, right? We can see, okay, as you go down the hill into the valley, you can see some quite high pressures here. But then as you go back up the hill here, it gets quite low again, 15 meters, the same up this point. But this in itself is, without any flow through it, you're not actually seeing any energy loss as that water comes through. So we want a way to be able to import the demand into the system quickly. So in Epanet, you actually had to manually write in the numbers for each thing. You had to like count how many customers are around and add the amount of consumption that we estimated at the point. Not really scalable. So I'm going to show you a feature that we do is we let you bring in data from the customers, the meter data that they've got. I'll quickly show here, bring this in. It's basically just a GeoJSON file, like a GIS file that shows the location of all the houses. And in there, we also then like say, okay, how much water do they use a day? So we're saying, okay, they're using about 500 liters a day. And we're going to say, okay, we're going to replace all the existing demand with this demand. And you can see we've now loaded in all the customer points. Am I crazy? What's going on? Why hasn't this come through? Oh, yes, there they are. Oh, I think it may be because I have this custom layer on. Let me just change this. Yeah, here we go. Now we can see, you can see how each of those customer points is connected to the system. And if we run this model now, we can see, okay, now there is some actual flow going through the system. So very quickly, we were able to draw out a network, add the customer points, and then be able to quickly represent both the pressure throughout the system and the flow. So now if we put on this flow, we can see, okay, which way does the water move through the system? There's not a lot of loops in here, but we can sort of see how it's spread about and then if it has any effect on the actual pressures throughout the system. So yeah, once again, relatively simple. The next thing we can do is at this stage, all that demand is actually coming from the tank. So we have the big tank on the top of the hill, the water comes down, it's all the pressure from gravity that supplies. But obviously the tank doesn't have an unlimited amount of water. So we need to use a pump to push that water back up into it. So we saw that we had the well here. And so we're going to quickly sort of design a pump. We're going to figure out, okay, what size pump do we need to supply that water up there? So what we'll do is we'll take it's called a reservoir, but it's like an unlimited supply of water. And we'll say, okay, this is like where our well is. And what we'll do is we'll draw just a short section of pipe here, and then we'll draw a pump. And this pump will take water from the well, which is supplying water at ground level. So it's basically the supply from the ground, and we need to be able to lift the energy from the water from this ground all the way up to the tank, and then also supply all the customers. So the way that you do this is you need to look at, okay, what is my elevation here, which is, sorry, let me click. Oh, with the head, you're saying, okay, I'm supplying about 385 meters of head. And then we need to basically lift it up by 325. So I'm really bad with math. I'll just, because I don't want to make a fool of myself. 55, yeah, 40. We have basically lifted 40 meters worth of head or pressure to get up to that tank. But we then need to also be able to supply the customers. So the way that we can do this is, I mean, you can start making guesses where you say, okay, well, we want to roughly put 10 liters in there and we need 40 liters of design head, but that doesn't account any of the friction losses that go into the system or the consumption. So if we just started making guesses like that, let's see what actually ended up in the tank. Oh, it worked, right? You did put something in, but you're only putting 8 liters a second. You wanted 10. So you've got to figure out, okay, what parameters for this tank do we need to make it be able to fill 10 liters a second and still supply those customers? So you can do a little trick in EPA where you can turn this tank off. You can put a demand at this location to say, okay, I want to be able to take 10 liters a second from this supply into the pump. And then you can actually put a negative number for your demand on Ethernet, and that will push that water out of the system back into it, right? So that normally we use a positive number and that's taking the water, but if we do negative, it pushes it in and forces it. So if you then do that, you'll look and see, okay, if we look up here, that the water has to go somewhere, and it's all going to end up going into the. Did I do that right? Where is that? Did I do negative 10? Oh, what have I done wrong? Anyway, this is what happens when you do a live demo. I'm not sure what I've done wrong here. But the idea is run simulation. Let's see. Oh yeah, now it's gone in for 10, right? And then basically the idea is you figure out, okay, the difference between what we've got these values of head between here and here is the actual design value that we will need, the amount of energy that we'll need to put in the system. So if we look at this number, 426.695, take away whatever this number is here. Um, oops, come here. What was that? Take away 385.599. So 40, let's just put 41. Maybe the 41 is going to be enough to do it. Do 41 and 10. Oh, and then you have to make sure you turn the pump back on, get rid of these extra things that we didn't want before. And then hopefully, fingers crossed, if you run it, should now be, oh, what am I doing wrong? Maybe I didn't add the numbers up. I feel like a time pressure. Um, oh no, it was 10 plus everything else. Oh, sorry, I was going to actually add the extra flow that was already going through there. Anyway, the idea basically, if you follow the example, you're not under a huge time pressure like me, is that you can end up like designing the pumps so that they supply enough flow and then also their customers as well. I will end this here, but I will say in the other example, if you keep following it along, you can actually design the rest of the system and then put a PRV and quite a few other things. And so it's a really handy guide to be able to like design a real system and then actually do some like real use cases. I know sometimes when you do these, it's just theoretical, but we wanted to give examples where it was realistic. So with that, I know that was a very speed run on some learning, but I wanted to show the tool. I'll stop a breather, and then maybe we hopefully have a couple of questions that can be asked.
Yes, thank you so much, Luke, for that discussion and workshop. How's everybody feeling? I hope everyone's doing well. And yeah, there's also enough time for them, and we've also shared the work example that they can work on independently. We do have a few questions, Luke, so I might get started. First question from Pep Strinchon from Type. So can EpanetJS handle water quality modeling like standard Epanet, such as chlorine decay and similar simulations?
I feel a lot of the answers I'm going to give are going to be of similar vibe to this. Not yet, but soon will be the answer, right? So we really focused on trying to get the core experience right, trying to get it very performative, working really well in the browser. And so we focused on steady state, so these single snapshot simulations and not extended period times or water quality. But we will move into water quality. It just ends up opening a big can of worms to get to that point because you have to end up supporting quite a few features. But this idea of water quality is yes, definitely we're going to do it. And then also the other thing that many people miss out is something called Ethernet MSX, which is this advanced water quality. We also want to bring that to the browser. So it might be a few months to say the least, but definitely our intention is to bring chlorine decay, byproducts, water age into this application as well.
And I think just a follow up, Luke, on that, like for added features, are you looking for people to test it once you started adding these new features?
Yes, yeah, definitely. So we release quite frequently, like almost every day we'll add new features. And if you look at GitHub, you can see what we're adding. The way that we'll do it is with some features, we'll release it first to people who register or a keen user. So we have the ability to turn on and off features. So if you're an active user and you provide suggestions and say, oh, I really want this feature, we try to keep note and then sort of give it to people early. But just in general, one of the things when you register, you'll get an automated email from me just saying thank you, like, and let us know of anything. And yeah, really the biggest thing anyone can do is test the app and provide feedback on how they found it, any bugs, or what they would like next.
Okay. How about group edits, Luke? Does EpanetJS support that?
Yeah, it's at this stage, no. At this stage, everything is done locally on your own machine. So even though it's in the browser, there's nothing actually in the cloud. The application runs in the browser, but you're actually editing local files. Soon we'll bring a version in that you can store things in the cloud and then share that with others. And then there's that question on, okay, do we make it a collaborative thing like Google Documents, or do you make it just something where maybe you have one person controlling it, but then you have others who can view and add comments? The collaborative part is very complicated, technically challenging, and we don't know if it's truly necessary, but we definitely think at least having the ability to collaborate, at least in comments and reviews, and be able to run simulations together makes sense. So, if you've got a use case where you think group editing makes sense, we really want to hear it before we get to that stage. We think it's going to be very challenging, but maybe there's a use case we don't know that it makes sense.
Mhm. Very well. And the question from Ron, can it do EPS? Can it do an EPS?
Yeah, so extended period simulation. So
Mhm.
the simulations we saw were steady state, where it's just a single snapshot in time, where like almost you've taken a picture of the network. Extended period simulations are where you can run the simulation for 24 hours or whatever, a set of snapshots one after the other. Not yet, but soon, once again. To do support extended period simulations, you need to be able to support demand patterns, curves, controls, graphing, tables. And so, like I said, it's this real big can of worms of features. So we're trying to get the, GIS import, customer demands, this experience of building the network working really well before we open up to the extended period simulation. But that is definitely a target that we want to get to soon. I would say
Okay.
that if we would want to be able to make it really easy to build a model in here, and you can always save it back to EPANet or other tools and finish the job that way as well. We think that's going to be the workaround for a lot
Mhm.
of people. Like get moving really quickly and then drop out to EPANet and add those patterns and things will be the best use case for most people.
I see. Yeah, that's a really good insight in terms of the workflow. Yeah. So a question from Aldrin. How about to simulate open channel flow? Is it available or to be added in the future? Mhm.
Yes, that's usually the another common question that people ask. So the cousin of EPANet is SWIM, which is the open channel, the stormwater and sewer. Um, there's a couple of challenges there. One is that stormwater and sewer is much more complicated than the pressurized system. So it's much easier to tackle the pressurized system first, get that working before you get into the much more complicated part of the sewer simulations, both that there's more parameters, more things to do. The simulations are bigger and take longer to run. And the really strong sticking point is I've never run a wastewater simulation in my life. So if I was going to do it, I might be the wrong person to take that on as the first challenge. I've always done pressurized, so I know it really well. So our decision was to like, let's focus on getting this really, really, really good. And then once we've got a little bit of traction, we know we can probably bring on somebody who understands the wastewater. We can talk to those customers with relationships and then solve that problem. I'd rather get something really, really good than to deliver something that's, maybe falling over itself, or I don't truly understand the problem. But yes, I promise you very soon we'll do that, but we're going to focus on the water side first.
Mm. Okay. Well, we have a lot of people in the call from the wastewater side of the utility. So yeah, they're excited. I know. And
Yes.
if you need any
Yes.
feedback or suggestion. So one suggestion from Paul, he's from Pipe. So before modeling the pipe, there would be a feature to choose the diameter and roughness. Is this something that you are already thinking of as an improvement in the current version of EpanetJS?
Yes, I mean, I do apologize because we went quite quickly. When you put down the pipes, it gave a default diameter and roughness. And so you can go back and change that, but we know that's a little bit tiring, constantly changing it. So the feature we're looking to add is almost like a toolbox of standardized pipes and sizes. So before you draw it, you'll be able to say, okay, I'm drawing a 100 millimeter pipe that's a polyethylene, and it would automatically set up the roughness for you. And so as you draw, it's there, or you can select a range of them and change them to like your catalog of known pipes and sizes and roughnesses, so that that becomes more of a managed experience for you. So you can do it at the moment. It's a little rough, but we have some plans around making that a much nicer experience. And this is the idea of getting that building and drawing the network well before we move to the more tricky stuff, but definitely something we know we can improve as well.
Perfect. We are running a bit over time, but if you have anybody who is in this call, if you have any more questions, just put them in the chat box or send them to philywp@gmail.com. We'll make sure to forward it to Luke, have it answered, and then send it back to you so you can also have a read as part of the kit after this webinar. Are you open to having like a post-webinar session photo op, Luke? So
Yeah,
I'll ask
of
people
course.
to,
If people
yeah,
want to
yeah,
reach out to
people are
me
here.
or anything, yeah, whatever they need. If you want to see the work that we're doing or ever get in contact with me, I post quite frequently on LinkedIn. I'm trying to be very open with this building this tool. There are options to contact either me there directly or even book calls with me. So I try to book Mondays as my session for just conversations with people. People in the Philippines or that side of the world, the timing could be difficult. So you could always reach out to me and we could find a mutually acceptable time. But yeah, I'm an open book. I want to share everything I can. So any questions, comments, anything, yeah, that's the most helpful thing that we can get at the moment. So whichever way, I'm happy to keep continuing it.
All right. Thank you so much. Okay, I'll ask MJ. We have a post webinar survey. If you can start that poll, MJ. And then I'll quickly ask everyone who's open to it if you can like switch on your cameras and we'll just take a group photo before we end the session.